Hello, everyone. Welcome to the next joint meeting organized by Washington Quantum Computing Group and Quantum Computing Group's meetups from Warsaw, Harrisburg, and Toronto. And today we'll have a great and interesting lecture given by Laura Gatti, Rafael Sotelo, and Machin from QuantumSouth. And the title is Quantum Computing Applied Cargo Load Optimization. So we'll start from Rafael, and if you have any questions, please post your questions on our chat. And at the end, there will be a Q&A session when we'll ask your questions, and hopefully our speakers will give you answers. So let me just stop sharing my slides. And Rafael, the Zoom is yours. We can start. Thank you for accepting our invitation, for giving this talk, and
thank you.
It's our pleasure.
Well, Pawel, thank you very much for the invitation. Thank you, Shahin and Terrill, for organizing these great events. Hello, we are QuantumSouth. We develop solutions in the quantum computing area. We work on optimization applying quantum computing. We were born at Universidad de Montevideo, University of Montevideo in Uruguay. And we were accelerated at IOT Tribe. It's an accelerator in the UK-based accelerator. And well, thanks again for the invitation. We are honored to be with you today and excited for being part of the global quantum community. We frequently attend Washington Quantum Computing Meetups. Well, Washington Quantum Computing and Harrisburg and all the communities that organize these meetups. And particularly, we were invited as moderator in this interesting previous meetup with speakers from Zapata talking about machine learning. And it was excellent. So thanks again. So here is our agenda for the following minutes. I will talk about our journey, about what is QuantumSouth and what we have been doing for these 2 years. Martin will talk about the problems we are working on now related to cargo and the approaches we are having to different operators. And finally, Laura will go technically deeper, and she will explain about our technical approach to air cargo load optimization. He will expand that explanation. So we started our journey in 2019 at CES. This photograph is at CES 2019 in Las Vegas. This is the booth of IBM. This is Robert Loredo, an IBM Quantum Ambassador. Well, he was invited and kindly accepted the invitation to visit Universidad de Montevideo. He offered a 3-day workshop for students, for faculty and professionals from the industry. We were exposed to...
Claro, que as discussões de Brasil e turma, então tem uns.
Okay, we can continue. I've just muted one person.
Thank you for that. Well, as said, we were exposed to IBM Qiskit platform during those 3 days. You see, there were a room full of people. Some were students, some were professors, some were from outside the university. And finally, well, the idea arose to participate in the Airbus Quantum Computing Challenge. Well, we considered that. We studied the problems. Airbus wanted to explore the use of quantum computing in 5 complex aviation problems. they were, as they say, they were between, those problems were between the hardest faced by the industry. So it were 5 problems. We addressed this one, problem number 5, aircraft loading optimization. So we make a multidisciplinary group. We balance the decision, study the pros and cons. Well, finally, our decision was go, and we started with this problem that was stated like this. Let there be N package to be transported. Each package A has a weight WA and a volume VI, and the vehicle has a maximum load capacity N and a maximum volume B. So the objective is to identify the optimal selection of the individual packages to be transported that maximizes the weight transported in each trip, subject to the load and volume constraints of the given vehicle. Given the exponential increase in the number of possible combinations as N increase, the problem poses a serious challenge to be solved by classical means. So this is a combinatorial problem. You see that there is an additional complication, that is, there are different volumes. So the Airbus gave sample data sets. Well, we worked on that, and there were some other complications to that to the center, to adjust the center of gravity and so on. So we submitted finally on October, by the end of October 2019, we submitted our proposed solution. It was inspired in the well-known knapsack problem, which is NP complete. We conceived the creation of a Hamiltonian representing the problem. We use the variational quantum eigensolver, VQE, an algorithm present in some quantum computers, as you know. In particular, we use IBM Qiskit platform, libraries, and testing environment. Laura will talk more about this, but you will see that here some hints. I mean, we propose IC models for adiabatic quantum computing, and the requirement in qubits is, well, n plus log c plus 1, which n and c being, n is the number of items or containers, and c is the slots, the number of slots, the aircraft capacity. So you can see here that so you can see that now with systems that are, in general, available systems are under 15 qubits or 50 qubits, the more the high end available now. Well, this is right now we can approach small problems yet, but in the future there will be we will be able to tackle larger problems. Well, so we aim to provide a building block leveraging quantum computing to bring innovation and better solutions compared with current approaches. So the Airbus Quantum Computing Challenge around the world was a success. There were more than 1,000 inscriptions from more than 70 countries. 160 teams were actively working during the challenge. And finally, there were 36 submissions. So this is from the MIT Technology Review. This is Terrill from Airbus, the organizer. He was presenting at MIT Media Lab by the end of that year. So we will go a close up to this image, and you will see the diversity of regions and organizations that enrolled in the challenge. So we are from here, from Uruguay, but you can see that people from all over the world. So we can highlight people, individuals on registration from the US, from Canada, from Europe, from India, Australia, China, Russia, and well, also from Latin America. So these are official numbers or data from Airbus. So finally, because of the pandemic, the results were announced 1 year later, the 12th of October 2020. So we were one of the 5 finalists for all the problems. We were one together with people from the Netherlands and France, a team from Italy, another from Germany, another from China, with the team Universidad de Montevideo. So this gave us, so this encourages us to continue working. We were already during the year, we continued working and developing our solutions and our commercial approach to final customers. But you can see the jury that the jury was a very qualified jury, certainly. Well, they told us about our proposals that they were impressive proposals with high potential. So, well, let me introduce now. This is our team. We are also the founders of QuantumSouth. We are professors of IT for mathematics and physics. We have also students, engineering students, and we also have professionals from the industry. So after that, we continue as a sub products of our participation. We in the Airbus Quantum Computing Challenge, well, we presented our work in different international conference. For example, here is in Portugal at the International Iberian Nanotechnology Laboratory. This was in October 2019. Well, and all over the world, really. Here is another from Chile. These were the first conference we attended and speak at, but during the 2020 and 2021, we continue with that. But this is a milestone for us. During June and July 2020, we participated at IOT Tribe, that is a UK-based startup acceleration. So that gave us access to people, to funding opportunities, to events, both to attend and to present. So we received technical and commercial mentors. We received pitching training, and we developed a business plan so to focus our strategy. We continue working and closely with IoT Tribe, their managers and collaborators. So in our business plan, well, this is QuantumSouth right now. QuantumSouth works with complex optimization problems for cargo in airlines and ships, leveraging quantum computing software. Same restrictions as today, same limited time, software optimization through best practices and extended space linear programming. So the goal is to achieve better results than conventional solutions available today and help companies to improve revenues and reduce costs. So we have been talking about airline cargo, but that is what we are working right now. But the same kind of problems applies to maritime cargo, which is even larger. So combinatorial problems are larger here. So we find here bigger opportunities, but we will tackle them once quantum computers get bigger size. We are now working on airline cargo. And financial services, we are also working on it currently, and we are, because it has some similarities to the airline cargo. So let me tell you a bit about the business. These are official figures from IATA and from Boeing, public numbers from 2017. So the forecast for this is the freight ton kilometers. I mean the unit of the business is the freight ton kilometers. How much tons you carry, how many kilometers you freight, a number of tons. So this is the number. The important thing is that it was expected to continue growing, and this is the revenue, air cargo revenue trends, and it was from 2007 for 10 years. It was with a little growth, but it was around 100 billion in revenues. Okay, that is enormous, isn't it? But we found this. Look, these graphs, the white graph and the white axis is passenger load factor. So if you follow the white graph, the white line here, in 2017, it says here, the passenger load factor was 81%. It has been growing for 10 years. In black is the cargo load factor, and this is its axis. It has been around 50%. You see here, 50% for cargo load factor. So we find here an opportunity. So for each 1%, say in the cargo load factor, we estimated that the revenue can be increased by 1.6%, keeping the cargo yield constant, or save expenditures by reducing by 1.6, and the revenue remains at the same level. So we find that maybe we find here an enormous market with an enormous opportunity. So how is this being done today? A lot of restrictions with limited time, software optimization, so classical means, limited space linear programming. So our solution is a software product integrated to legacy systems that, based on cargo to be dispatched in an aircraft or ships with limited capacity, will provide the best allocation based on cost and revenue restriction. The core optimization algorithms are based on quantum computing technologies. This is the architecture of our product. We need to integrate with legacy systems. We have here at left. Then prepare the data of each specific run of the algorithm, apply it to a particular instance of the problem. And finally, send it to the quantum computer to run the algorithm based on BQE to obtain the best solution. So the business value of this is, first, financial, increase the load factor and cargo yield, and reduce asset utilization by optimizing fleet usage according to the demand. And operational, to process automation through new optimizations and less leverage on skilled headcount. This is our timeline for the next years. We are developing the product and offering consultancy right now. We plan to make a proof of concepts and pilots. We will talk more about this in a few minutes. 3 years from now, once quantum capacity is available, that depends on the manufacturers. Our estimation is 3 years from now. We will deliver product, either by software licensing or software as a service. So right now we are approaching airline cargo companies and banks and other actors in the financial services to work in these two lines, to make proof of concepts and pilots in these two lines. We are integrated globally. During these 2 years, we have worked, participated in many events. For example, we have been organizer of the workshop on quantum computing entrepreneurship at the IEEE Quantum Week. We participate in many events in quantum technology all around the world, and in particular, we were organized of Quantum Latino. It was last June, the first large event about quantum computing in Latin America. We got more than 1,000 registrants. It was 3 days. It was excellent to bring the quantum community in Latin America, which was not very active. Well, we have a lot of connection. It was a great event, both for academia and industry. We have continue working. We are continue working on that. So that is part of our role on building community worldwide, in particular, and in Latin America. So we also participate in different challenges in like Singapore Airlines Challenge, Slingshot 2020 Startup Competition, and so on. And what regarding the manufacturers, we have worked with platforms from many vendors. From IBM, we worked with Amazon Web Services Bracket, with D-Wave, with Cambridge Quantum Computing Ticket, with Microsoft. I will make a note here later. We have a special relation with Microsoft. And with IonQ, we are also working right now with them. We have a special agreement with Quantum Brilliance. It's an Australian company who makes quantum computers for room temperature based on diamonds. So we have a special agreement I will talk about in the next slides. And we are also in contact with other major vendors like Honeywell, Fujitsu, Google, and Atos. So this is our agreement with Quantum Brilliance. This is a sample of, has had, echoes in the press. This is from the Quantum Computing Report, but there are many others. So we are working closely together from December last year, in demonstrating the quantum advantage can be achieved with fewer qubits in logistic optimization applications when combined with QuantumSouth software. So our technical team is working close with Quantum Brilliance technical team, and we are currently accessing POSIX Supercomputing Center in Australia and working with the Quantum Brilliance quantum emulator, which is QBQE software. So we also have commercial cooperation, exploring applications in logistics and other fields which require combinatorial optimization, fields like mining or some others. So for example, we are part of the Quantum Pioneers program at POSIX, at this supercomputer center. At the first event of this, we participated together with people from Australian universities and we from the industry. Well, let's go back to another provider, who is Microsoft. Our mother university, this is University of Montevideo, is member of the Microsoft Quantum Network. It is one of 20 universities in the world and the only one in Latin America, being part of this community of pioneers. So that gave us access to a curricula based on from developed by Microsoft and University of Washington. A course which Laura will be later here has been the main instructor. It was developed, it was delivered under Microsoft Quantum Katas. We have undergraduate students and master students, research oriented. So you see everybody's happy at the last day of classes. But we have trained more than 30 people in developing quantum computing software. So the course is ready in this semester that will begin in August. So it has been a success, and we have here good and clever potential collaborators. So about QuantumSouth, we completed the seed round provided by founders, by family and friends, and by the Uruguayan National Agency for Research and Innovation. And together, QuantumSouth and Universidad de Montevideo, we are committed to build a vibrant global quantum community and a Latin American also quantum computing community. We have postdoc opportunities, research opportunities for graduate students, and internships for graduates and undergraduate students. I will tell you a little more about this. We have now, we are ending an internship. We not only have Uruguayan students, but also people from India, for example. We have a master student ending an internship. He has been all the semester with us. He's ending next month his internship with us. He addressed, Martin may talk more about this. He addressed this kind of problems we are working on. And we also have interns from PhD student and master graduates from Colombia and Mexico, Ecuador, Chile, and from Argentina, from many countries in Latin America are also working with us, and we are approaching different problems, not only in air cargo, but also in machine learning, applied to predicting price of different products, for stocks and so on. Well, Martin, do you want to continue talking about our working lines and results? Are you there?
Yes, I'm here. Thank you very much, Rafael. So I'm Martin Machin. I'm one of the co-founders of QuantumSouth. And today I dedicate a lot of time approaching potential customers, air cargo companies, doing business development and creating awareness of this solution and how this technology could help the business of the companies. And also connecting with the different quantum hardware partners that are helping us to test our solutions. So everything that Rafael mentioned that started with the Airbus challenge, where we created a basic algorithm, we started to connect with the industry in detail. We started to adjust to each particular business scenario, because we have different air cargo companies that some are freighters completely dedicated, business units completely dedicated to air cargo, others that mix cargo with passenger flights. They have different routes around the world. There are airports with different demand for cargo. So there are multiple aircraft providers, different models. So there are different things that we will be adjusting the original algorithm that we have to each particular problem. And also testing in different technology platforms, because although we started creating the algorithm in IBM platform, we aim to be agnostic with the solution. And in parallel, we have been testing it and adjusting it to different platforms. So we have been replicating the algorithm and adjusting in the wave, in IonQ, in Quantum Brilliance. We're working with Honeywell. So several platforms to see how we can scale the problem. We are limited by the number of qubits. We are limited by the noise, by many things. So what we want to do is to test how it behaves and try to bring this solution to the market as soon as possible, based on the restrictions that the business applies. One important thing that Rafael mentioned was the percentage of load factor in the air cargo industry that is far behind the passenger load factor. Currently, that data from IATA in 2017 was 50%, and that have not changed much. That's the average. So that means that there is a lot of opportunity to improve those figures. But also that means that the digitization of the cargo sector is not at par with the passengers. So when we go to the air cargo companies, they still have a lot of things manual and they not necessarily have the latest things. So we found that they have a lot of problems to solve, and loading a container in an aircraft, optimizing it is good, but also they have a lot of problems that we have to observe and analyze while embedding this in their normal operations and with their IT systems. Because Rafael, for example, showed you in the charts that we are getting the data of the containers that needs to be loaded in a particular flight. And we map this data to the quantum algorithm. We send to the quantum computer. We get the results and give it back to the business. But the journey starts earlier, much earlier, because customers will connect with the cargo companies. They will enter their orders through different channels, through the legacy systems. That data will come to the systems of the companies. They will look at the destinations, how many times they travel to a destination, and they have several best practices, like, for example, they have a company, a customer that rents periodic cargo to a particular destination. So they have pre-filled the aircraft with that recurrent customer. But the challenge is how to optimize with those cargo requirements that are not clear, that are coming. And I'm not sure if the aircraft will be completely full or be empty. So what we are saying is that we could help the companies to increase the revenues with the same fleet or deliver the same with less gross fleet. We can cancel some aircraft if we can know that in advance and apply that. So, well, this particular problem that is based in the NAXA problem, and that Laura will talk extensively, all the particularities of the mathematical problem and how we are addressing in the quantum computer, starts from the moment that you have already packed all the containers that could be going to the aircraft, or at least you know what is there. So we have tested this scenario in IBM, we have tested in D-Wave, we have tested in IonQ, in quantum brilliance with different number of qubits and exploring what are the possibilities. So far, we are exploring, and Laura will talk about how the BQE algorithms behave with that. The best results that we have today are in the D-Wave platform, that we could organize more than 40 containers in an aircraft. And this is something that we need to compare with the system that the companies have. But when talking with companies, they not necessarily are using something that we can show, okay, this is better what you have, because there are so many problems that they not necessarily have something to do the same thing. So we need to work in more things. And the first thing that they told us was, okay, it is important that we have the aircraft complete with containers, but we have another problem. Rafael, if you can change to the next slide, that is how we load a container itself. That takes us to another problem, because the customers send small packages of different nature to the warehouses of the air cargo companies, and they need to prepare this in advance. It is very important to utilize at maximum the capacity of these unit load devices that have many formats. Rafael showed you an example from Airbus that we have 3 different types of ULDs, but actually there are more. Some of them are structured and others are not structured. You just load things on top of the other things and must comply with the restrictions of the aircraft, with the share limits, with everything. So this is another problem, because you lose a space in the aircraft. It is not only because you left container space, but also because you have space idle inside the containers. So this is another problem that we started to work that has more variations, that have different complexity than the one of loading the cargos itself, because you can see there could be even more packets. They will have more different sizes, irregularities that you can accommodate things. And we are using different mathematical models to tackle this problem and to solve that. So this is another thing that we need to help. We have the opportunity to help the companies. And this will not only apply to the air cargo companies, this will also apply to truck companies, ships, and everything. So this is how the process of cargo is going on today in the cargo companies. And in the next slide, there is another problem that we started to work that was anticipated by Airbus in the challenge, a problem that we analyzed at that moment, but decided to take another one. We are evaluating now how we could help with the fuel optimization. Today, the cargo companies can leverage on historical data. So there are a lot of things to be done with conventional systems, by analytics or even machine learning, just analyzing how the fuel consumption has been doing in different airports. So far, that is good. And there are still many companies that need to adopt these conventional solutions. But this that we are working is a different one, because this attempt to optimize the consumption in particular moments of the flight, and particularly those flights that are not long haul. I would say, for example, those flights that are transoceanic, for example, that they have a lot of hours in the cruise time. Okay, the climb and descent is not so representative in terms of the total flight time and fuel consumption. But when flights that are shorter, that takes, for example, 2, 3, 4, or 5 hours, the impact of the climb phase and the descent phase are very important. And the aircraft takes a lot of effort and fuel to do the climb. So there is a mathematical model for the climb, and we are trying to optimize the trajectory of this. So this is another area where we could also help in the aviation problems. So to summarize this, Rafael, in the final slide from my space, this is what we are finding in the air cargo process, what companies are doing and how they are operating from the moment that a customer books some cargo. That data goes to operational software. As you, as an air cargo company, you are seeing what is coming, so you can work on the cargo schedule planning. But there is another problem that once you need actually work with the optimization, the customers may deliver something different to what they said. So they said that they will put 1 cubic meter and then they come with 2, or something is delayed, or something happened. So there are a lot of activities related to review this cargo schedule planning. So these are a lot of uncertainty that leaves you to work in a short, limited time to do the optimization. So you need to work on the ULD load optimization first, as I mentioned. And once you have these containers or the projected containers that you may have been foreseen from the operational software, you will execute something related to the aircraft load optimization itself with the containers. All these things need to interact with the operational software handling the cargo and the billing and all the revenue management factors, but also with the aircraft operational details. So there are many software vendors that the pilots of the aircraft are connecting and putting what is the information of the flight, how loaded it is, what is the configuration. So all that information needs to be contrasted with those systems that are being used and provided by the aircraft manufacturers or third parties. And all those things must be mapped there. I also would like to mention that in the load optimization, there are other restrictions that we need to consider, like there are merchandises that may have priorities for urgency, or there are things that cannot be mixed, or there are dangerous materials that have to be placed in a particular area, or there are animals. So you may have to pre-allocate a lot of things and then run whatever could be optimized beyond these initial restrictions. And then once the aircraft is ready, everything is okay, the pilots could leverage this climb fuel optimization techniques in the future using data from the weather and everything. So this is what we are seeing as opportunities in cargo. Each company will have their particularities. So we come with a basic structure of problems, and we have to adapt it to each scenario and particularities and degree of digitization and processes of each airline. And that it is, and we expect that we really could help the cargo companies in the coming years with these new technologies. And now I will hand over to Laura, that will talk about the technical details of how we could organize containers in a particular aircraft.
Thanks, Martin. Thanks, Rafael. Hi to everyone, and thanks to be here with us. I want to share with you our technical approach of the cargo problem, of the first problem that Martin talked. And I will start with the first idea that we managed, that was the classical knapsack problem, as I imagine you heard about it. The classical knapsack problem is to maximize the values of a total load put in a sack, but taking into account a weight restriction that we call C. In other words, in the knapsack problem, we want to put all possible objects, but without exceeding a given weight. So for the mathematical formulation, we have for each object a Boolean variable x sub I that can take the values 0 or 1. When the variable takes the value 1, it means that the element I was actually put in the sack, and if the variable x sub I takes the value 0, the object wasn't put in the sack. So this is a classical problem that we want to maximize the total value of some objects put in a sack, subject to a sum restriction and linear restriction in the Boolean variable xi that don't exceed the maximum weight that is given. So this problem is very similar to the problem that air cargo companies face, but with some modification. The main modification that we had to think in this context is that x sub I are the containers that we want to put in the aircraft, and each container has two main characteristics. The first one is a weight that we name as P sub E, and a maximum volume that we name as W sub E. So the aircraft has a maximum slot volume capacity that we'll name N. The problem is similar to the knapsack problem, but here we want to maximize the weight put in the aircraft, but we have two restrictions. The first one is the weight capacity, and the second one, the new one, is the volume capacity. So the problem is the same, but we add a new restriction in some way. Rafael, you can change the slide, please.
You see it?
Yeah, I see it right now. So this problem, the snapshot problem, that is a classical problem, has an alternative formulation that we can make with the Ising formulation. The Ising formulation is a statical mechanics model that is used for ferromagnetism effects, and the variables used to represent magnetic dipoles moments that can take the value 1 or minus 1. That is the spin up and the spin down of electron, for example. So it is a two-local problem. That means that in general, or in this context, there are no interaction of 3 or more spins. And in general, we have a term that represents a constant magnetic field that we call H sub I for each particular. So when we have a binary optimization, a classical binary optimization problem, we can change our X sub I variable to classical Boolean variable to some way quantum Boolean variable by transforming the variable into, with the change of variable, to the using the identity minus the C Pauli gate applying to the I container. For example, we can make as a Boolean variable, and with this trick we can form easily the Hamiltonian of the snapshot problem. The Hamiltonian of the snapshot problem that is right here has two principal components, the H sub A and the H sub B. The first one, H sub A, found it has the property that represents the restriction. It's a penalty in the problem when the restriction is not accomplished. But when, sorry, as you can see in the second equation, we have two parts of the penalty. What this equation can be interpreted is like is easy in some way. We put the weight condition C as a quasi-binary representation of C. That this means that we write C in a binary representation, and then we rest to this term the total weight of the containers that are actually put in the airplane. So when the total weight is greater than any value greater than C, this term can't be zero, and we add to the Hamiltonian a positive term that is opposite to the sign of the optimization part, that is H sub B, that we can see here, and works in this sense. The optimization has a negative value. When we add a new container, the Hamiltonians sum a negative term, and when we want to add the most containers that we want, but when we put a lot of containers and the total weight is violated in some way, this term HA functions as a penalty and some positive terms to the total Hamiltonian. So in the next slide, we can see how this snack classical problem can be mapped to our problem that has three terms, because we have the terms that we want to optimization, that is the load optimization, but we have two other terms, that one is the penalty for violating the volume restriction, and the other is the penalty for violating the weight restriction. So here there is an easy example to understand how this works in a particular case. Suppose that we have 4 containers that have weight 5, 4, 2, and 3, and have volumes 2, 3, 5, and 4. The max volume is 8. Sorry, the max weight is 8, and the max volume is 7. So the solution of this Hamiltonian will be the eigenvalue with the lowest energy of this Hamiltonian. We want to find the eigenvector that has associated the lowest eigenvalue of this Hermitian matrix. So in this case, for example, if we put the container 1 and container 2, we have a total weight of 9 that is greater than the maximum weight that we can take, that is 8. But if you see the volumes, we have a volume of 2 plus 3, that is 5, and is in the range of the volume restriction. So we want to find which combination of these containers is the best for this problem. So in this case, we have to select the container 1 and the container 2. If we see this this illustration of containers as piles, we can see that if we choose containers 1 and 4, we have 5 and 3 of weight, that is a total of 8. So the maximum is respect. And in the volume, we have a total volume of 6. So there is one space that is not used. So the slack variable, so the solution is the first one, and the slack variables functions as a compensation, for example, for the volume, that the total volume plus the slack representation has to be exact the volume restriction in this case. If the volume restriction is not respect, this slack can't compensate this problem, and this term, or the term A or the term A or the term B can't be 0, and this is not this was not a good solution. Can you change the?
Okay.
So with the first part, we select the containers that we want to put in the aircraft, but then we have to face other problems as the center of mass of the aircraft, and the shear stress of the containers put in the aircraft. So we can do as a cascade procedure to put now the containers into the aircraft. We just know what containers we will choose to put in the containers, and with a similar Hamiltonian in some way. It is more complicated than this, but this is a small representation of it. We can choose how to put these platforms in such a way that the center of mass is minimized and the shear stress is respected in each container. So this cascade procedure has a lot of advantages for us. For example, it's greatly reduced the amount of qubits because otherwise, if we want to solve the two problems in
one run.
Hamiltonian, okay, if you want to do all together in one Hamiltonian, we have the problem that each position would need an extra qubit to be represented. So this cascade configuration allows us to reduce the amount of qubits. Then there are other advantages as reduce the number of terms in the Hamiltonian, which as well we'll see for implementation, which, as we will see, for implementation of quantum computer helps a lot. And then there is a very good decision to escalate the problem for more containers in other models of aircraft. So, Rafael, can you change? So now we just have the Hamiltonian that we want to work with, and what we want to do is finding the lowest eigenvalue of this Hamiltonian. Our Hamiltonian has some properties that are important. In particular, Ising problems always have diagonal Hamiltonians, and the eigenvectors are the vectors of the computational base. So we want to find this vector of the computational base that represent the best solution. The eigenvector associated with the lowest eigenvalue will maximize the weight and will meet constraints. So the better the solution, the more negative that the energy is. If any of these restrictions, the weight or the volume restrictions, is violated, the total energy of the Hamiltonian will be positive. And this is very important for the different available technology that we can use. The first one is the approach of quantum annealings, that they are especially suited to specific optimization problems. And the Ising problems originally was thought to solve on adiabatic quantum computing, as, for example, the wave does. Then our Hamiltonian can be easily mapped using the Q methodology for use a quantum annealing. The other direction that we can take is use gauge-based quantum computers. Gauge-based quantum computers are the classical quantum computers, and there is a well-known algorithm that is the quantum phase estimation algorithms that solve this problem exactly, find the lowest eigenvalue. But the problem is that it can't be used right now, because the low gauge fidelity and the amount of noise that actually gate-based quantum computers has is not suitable for quantum phase estimation. So there are other algorithms, as the BQE, that we can talk about it in a minute, that are hybrid algorithms that takes a part that in classic computers, and other parts is solved in quantum computers. So in the next slide, there are representations of how BQE works. The BQE algorithms is a kind of hybrid algorithms that works with the Ritz principle, that finds that its goal is to find the lowest eigenvalue of a Hamiltonian H. This type of algorithms are based on the Ritz variational principle to prepare approximation to the ground state by using a quantum circuit with a small set of parameters that can be updated. So in the illustration, you can see how this works. The task is divided between a configurable quantum processing unit, the QP unit, and a classical processing unit, CPU. That the quantum processing unit calculates the expected value of H And then the ansat state obtained by the parameterized quantum circuit sends these values as an input to the classic optimizer running on the CPU. Then the parameters are updates, the thetas of this illustration, and are given to the quantum circuit for do a new repetition of the process. So here the main problem that we face to use BQE is how to determine this ansat of this quantum circuit U, that is a unitary matrix with thetas as parameters. And this ansat is which determines the performance of this algorithm. Why? It is because the ansat determines the search space that we can use to find our solution, determines the number of parameters, and the number of parameters has a very strong relation with the classic optimizer, that how they work, because if a classical optimizer has a lot of parameters, it's easy that don't work very well. So this ansat also determines the possible starting points, and it's important when we design the ansat that the optimal solution can be achieved by this circuit, although we don't know the optimal solution. So the design of the ansat is the key of the functionality of our algorithm in some way when we use BQE. So when we have you can change the PPT. Okay. So we have two options: or we use quantum annealings, or we use gate-based quantum computers. Quantum annealings has a natural way for the representation of our problem, and the difficult part of use it and set it up, it is the selection of the constant of each component of the Hamiltonian, because the K2 operation in the quantum annealing is the energy gap between the ground state and the followings. So the choice of the constant A, B, or C is a critical factor for its performance. In the other choice that we are working, that is using gate-based quantum computers in the NISQ era with these hybrid algorithms, the crucial thing is the election of the ansat, and when we have to design these circuits, each platform has some particularity that we have to manage to have the best ansat in each physical machine. So classical, so we have to, the problem using this approach is we have to manage to use very few qubits, and this is a big limitation in comparison with quantum annealing. So we are working in the two universe of quantum computing, and this is what I want to share with you. I don't know if Martino want to add something.
Yes, finally, we want to remark our final message, that is that we are open to collaboration with major industries worldwide to help them to be quantum computing ready. And we are looking for big complex problems to make proof of concepts and pilots, to study them, and well, problems that may bring the quantum advantage to industry and government sectors. So that completes our presentation. We are here for any questions that may be from the audience.
Great. Thank you very much for a very interesting presentation. So actually, we have several questions. So first, there were some questions regarding the video recording. So as Helen replied, the recording will be available on our YouTube channel, hopefully. So there is a link provided by Shahin. So thanks, Shahin, for this. There was also a question from Dr. Kumar Gautam. Interactions with two states in the presence of both, then how to decide right trajectory. And there is information about the magnetic field in classical cases in the form of BT equal to B plus, I guess it is delta BT. So when magnetic field interactions with an ion, then interactions Hamiltonian is changed. I'm not sure if I understand correctly this question.
No,
maybe Dr. Kumar
neither,
can,
sorry.
So maybe Dr. Kumar can try to reformulate it a bit. You can, if you are still with us, you can unmute yourself and ask your question, because maybe it was just a question regarding a specific slide that was presented somewhere at the beginning.
No, okay. Anyway, maybe reformulated or not, but we don't take a approach. We don't see the physical problem. We work on software. So we only approach some problems with the physics, but related to the particular computers we are working on, maybe the different platforms. If we all consider that only as some restriction that may be imposed by the manufacturer, but we don't deep into the physics phenomena, but we work on the logical side and the software.
All right. Thanks for this answer. So there was a remark from Dr. Georgiev. Isn't the last term of the previous slide the VE instead of PE? So I guess it was probably related to the Kubo formulation, because it was several slides back. I'm not sure. And again, if Dr. Georgiev can maybe tell us where exactly was this part, then that may be helpful, I guess, to verify it. So here I can see, because this is a knapsack problem, so we have just V, which is a value, and P is a weight. So in my opinion, everything is correct, but I'm not sure if this is this slide, or maybe it was the next slide.
I believe it was this slide.
This previous one. So it was even earlier, yes?
Sorry.
What was the question?
So Dr. Georgiev, can you please tell us where exactly was the problem? On which slide? I'm not sure if Dr. Georgiev is still with us, or maybe he can unmute himself. Or anyway,
But
if yes, maybe you can send
this is a classical formulation that is in every book.
So in my opinion, everything is fine, because we have this VI, which corresponds to the value, and PI corresponds to weight. And
can you hear me now?
Yes, we can hear you now.
So actually, it's two slides maybe after that one.
After?
Yeah, next one. Yeah, this one. So when I just wanted to be sure that I understood correctly, because the coefficients in front of C, I thought that it should be VPXI, VIPI, because this is what you're minimizing for. And I think this is just a copy and paste error, but I'm not
No.
sure that. That's why I wanted to ask.
We want to minimize we in such way as the constant is negative, we want to minimize, but in other way we want to maximize the weight of the problem of the total load. So the weight of each container is P sub I. So I think that is
But this is the two, A and B are the two constraints, and
Yes.
C should be the volume, which is represented with V, not with the P.
no, volume
No.
is represented with W sub E, and is the first restriction. We have the first restriction for the volume, the second restriction for the weight, and the load optimization is represented by the third term.
Oh, okay, and this is the full Hamiltonian, right?
Yeah, for this part, for the problem, yeah. This is a small representation because we added other parts to these penalties that works fine, but it's too long.
On the previous slide, you also had the variable V with subscript I. Wasn't that?
Sorry.
But
Yeah,
this was for the knapsack problem, so it's another problem.
But this is the representative for the classical knapsack problem when, here you want to minimize, to maximize the value, and in our problem we want to maximize the weight, not the value. But we can change our variable for maximizing and change. It is not a problem if we had another characteristic for each container that is the value we can put in the Hamiltonian without any problem. But in our first approach, we want to maximize the weight because the total weight is really correlate with the value that the earns of the company. So it's a first approach to the problem.
All right, thank you. Now I can see that there's quite a long question posted by Sebastian. So maybe Sebastian, if you can again unmute yourself, then you can just ask this question all of us, and maybe it will be easier. Or also I can just read it, of course, but I guess that it will be easier if Sebastian just.
Yes, sure. So hello everyone, and thank you very much for the interesting presentation so far. My question basically relates to the benefits. I mean, and I see that very often that when quantum algorithms are compared to classical algorithms, usually probabilistic algorithm on quantum computers are compared to exact solvers on classical side. So this, of course, especially for those cases where the underlying problem is NP hard or NP complete, this will definitely lead to a benefit on the quantum computing side, as you do not basically solve the exact problem but just an approximation. But of course, it's always possible to use approximation algorithms on the classical side as well. So did you do any comparison here, and are you able to outperform the classical meta heuristics like evolutionary algorithms and so on? And basically the question is, I mean, as far as I know in literature, there's not a single case yet where this has been proved basically. So did you do such a comparison?
So it's a very good question and a very conflicted point for us and for every person that makes quantum computing, not only us. We are not comparing these solutions with classical solutions. We are comparing quantum solutions from this for this problem. Why? Because in some way we are in most of case using simulators for solving our problems. So there is no a fair comparison with classic. In some way, we are using classic computing for doing our simulating our quantum computing. But the power of this approach, I think that is derived from two focal points. First, related to classic hardware, as you point, is the internal nature of quantum state that allow us to explore vast space search with exponentially fewer resources that we need in hardware in classical hardware. For the binary representations of these variables, we need very fewer results in compared with a classic search in all the space possible.
But maybe if I may jump in, I mean, the point is on classical side, your bottleneck is not size for NP complete or NP hard optimization problems. Your bottleneck is always time, right? So the important resource here is time. And the question is now, if you on a quantum side could save steps, basically, I'm not talking about wall clock time, but steps in the sense that you do not need an exponential number of steps for finding an exact solution, or if your convergence rate on a quantum computing side for the approximation is much better than on classical side. And that's exact. I mean, I see a lot of these approaches nowadays, right? And the result is always that it works. That's clear, right? I mean, of course, you can turn any combinatorial problem in a QUBO or in some Ising models and so on and so. No question about that, right? But the point is there any actual benefit?
Well, I think that I can't answer this question, because if you use the QUBO model, it is a way of solving. But if in the future we can run the quantum phase estimations and we don't have to lead with BQE and the hybrid problems, there is a clear advantage from quantum point of view. So what we are doing right now, my point of view, is trying to take the best advantage from the actual technology that we have. BQE has, we work a lot with BQE and has a great, it's a mess, because the classic optimizer don't match very well with the answer that we decide that we have to use. And I don't know, I think that for now it's not better, but it's the opportunity that we have of trying new things for the moment when the technology is mature. That is not now.
Yeah, but the characteristics of the involved algorithms do not change if you have better hardware. So even if you have a quantum computer,
yeah, but this is not true, because you can change the algorithms and
yeah, but VQE will not change, right? So the characteristics.
Yeah, VQE change a lot if you use different classical optimizers, or if you decide there are specific classical optimizers settled for VQE, then the results are extremely good when you compare one to other. I can share with you some graphics of our work if you give me a minute, that I have to find it, and you will see that there is drastically difference in VQE performance. So it's difficult to compare all the VQE performance with any in an agnostic way, and not talking about the classical optimizer that you are using. Give me a minute.
Okay.
And
yes, go on, Laura. Please, you can try to find it and present it. I'm not sure, but I guess that Sebastian also had in mind that rather the theoretical complexity and theoretical characteristics of the algorithm, like of the algorithms like VQE, independently on the hardware. Is it correct, Sebastian?
Yes, that's exactly the point.
Yes.
I mean, you're absolutely true. You can change the classical optimizer for VQE and QAOA and so on. But in the end, even if you have a fully error-corrected quantum computer, the computational characteristics of these algorithms and of the classical part do not change, right? So the question still, for me, I mean, I know that we cannot solve it in this call, but for me, still, for NP-complete optimization problems, I still do not see any benefit on a quantum computer, to be honest.
So I guess that basically what Sebastian also wants to say is that even if we assume that at some point we'll have quantum computers that will be perfect, then we cannot be sure that these algorithms like VQE may give us any advantage. Is this correct, Sebastian?
Exactly, that's my point.
Yes. So this is rather a question about theoretical analysis of these algorithms and their complexity, like time complexity, and not necessarily about the quantum hardware. Yeah, so I also understand that, of course, when we run these algorithms on the current contemporary quantum hardware, then of course the results will be even worse than.
But the advantage of this approach, I think, this is only my opinion, is that we can extremely reduce the number of parameters that the classical optimizers use. Mm-hmm. If you want to do the same in every direction without the classical approach, you have to use an exponential number of parameters to optimize. So if you can change the amount of parameters that you use in VQE is polynomic in the numbers of qubits. In numbers of qubits is polynomic in the size of the problem. So in some way, you have a number parameters reduction that can be, I don't know if it is, but can be a very improved in the classical way that we see these algorithms. Mm-hmm. Only for the representations, just give us an advantage. But I don't know, maybe I don't understand well the point, but I think that reduce the numbers of parameters that the classical algorithms have to manage is an improvement.
I mean, you're true. These algorithms on quantum side usually have a fixed number of parameters. That's true. So on classical side, that could be an issue that you have multiple or more parameters. That's true. But in the end, we're interested in either faster or better results, and that's what I cannot see.
Okay.
For NP.
I will share with you, but I don't find.
If I can jump in, this is Shahin. Sebastian, the way I see it is that we are in such early days of quantum computing that we don't really know what might lead to what. And if we don't really experiment, we may not have the insight that will in fact lead to the ultimate objective. So you're absolutely right. At the end of the day, we want quantum computing to be better than what we had before, and they promise to be better. But then if you don't really try it, we're not going to know.
Rafael,
that's true.
Can you share the other presentation of Quantum Latino that I will put the graphics, because I think that is easier.
It is in the same folder.
Yeah, it is in the same folder.
In the meantime, let me jump in and thank you, Sebastian, for the question. It's a very interesting one, and thank you, Shahin, for your comment here. I think we are all in the research process, and what we ultimately want is to find something that is better than what we have today. So typically, we are addressing NP-complete problems that the computation effort required for that makes it very hard sometimes to find the optimal solution or the solution. So we have been working for decades at this point of time with approximation algorithms that will find what could be a good solution. Like say, for example, there is an optimal, an absolute maximum that we not necessarily are able to find. So those algorithms let us to find some relative maximum that might not be the best solution. And this is because it is impossible to explore the entire space. So one expectation that we would have here with this quantum algorithms is try to explore a larger space that could help us to find those solutions. And the quantum perhaps could be faster, and we can do searches that are not practical in conventional system and find those solutions. So these are things that we are looking for to prove what is there. But lately appeared all those genetic algorithms and machine learning things that we go through other things that may arrive to another solution. But there is also no clue that they will actually find the best solution. So this is the expectation that we have. And whenever we go to a customer, either in the cargo space logistics or in the financial services, like optimizing a portfolio of assets with a similar thing, you say, we're asking, okay, how are you doing today? And what we want to do is to try to find something that will be better in terms of better solutions and also larger solutions. Like, for example, that you could optimize something that is much larger that could be done today. So that's the way that we see. And I think in the journey, we'll test many things, many algorithms. And we started with this. That was what the first thing that we had. So I appreciate Sebastian, and I appreciate your additional comments.
Can I share my screen?
Yes, sure. Go on, Laura.
Okay, I will do it. If you are looking my screen, here we have the BQE performance from, I think that was 200 problems similar to ours. We select in a random way the weights and the volumes of the containers, and then we use the median to perform this graphic. As you can see, the performance of BQE is dramatically different when you use, for example, the Nelder-Mead optimization, as when you use this one that is NFT, that is one that is especially made for BQE. I think that I have the paper. I will sell. Well, okay, then if you want, I can send the paper. It's optimized that was made by some Japanese people. And as you can see, the performance of BQE is dramatically different, which they are the same problem, the same initial points. So there are a lot of opportunity to improve the BQE. The BQE is in some way a great range of algorithms. You have to set the Hamiltonian, you have to set the answer for your problem, because any answer don't work in the same way. You have to for example, we choose to minimize the parameters, so we don't use entanglement in our approach. And this is a paper that we are working on it right now. And for this reason, I don't share all the results, but theoretically, they are not I don't know, but we can do better things that just are doing. in some way.
Okay, so Laura, do I understand correctly that these are just different classical optimizers used in the
they
VQ?
are
Okay.
they are
right.
the classical part of the algorithms.
All right, this the classical part. This is fine. So Sebastian, would you like to add something? Because I think that maybe we can try to summarize this discussion, and I can maybe add a few more sentences at the end. But if you would like to add something, then please go on.
Yeah, I mean, just what I want to add is here, that is, I mean, totally clear then if you change the classical optimizer in the VQE setup or for QAOA or any of these variational algorithms, yes, of course, you get a different performance, right? But still, the question is, if you, for example, if you say that NFT is your best classical optimizer here for VQE in that setup,
it is not a classical optimizer. It's an optimizer especially made to tailor-made for VQE. Don't work with other problem.
Classical means, in my opinion, that it runs on a classical computer, right?
Okay.
So you can use any other optimizer, any, I don't know, hill climber, whatever you want to use for the classical part. The question is, if you now compare your setup of VQE/NFT to the classical meta heuristics, for example, evolutionary algorithm and so on, then there's still an advantage of your VQE/NFT setup compared to the best classical known algorithms. And as far as I know, in literature, there's not a single case yet where this advantage has been shown. So still, the question is where's the benefit? And I totally get your point that now is the time to experiment. And because of the no free lunch theorem, yes, there could theoretically cases where the quantum optimizers are better than the classical optimizers, even for NP complete and NP hard problem. But most likely this will not be the case for all optimization problems. So yes, it's a lot of experimentation, I agree. But if we do not do at the same time a comparison to the best classical algorithms, we cannot claim that there is a quantum advantage in such a case, in my opinion.
We didn't say that we had an advantage from this point of view. We said that we can use quantum computing for solving this problem, and in some way, when you can use all the features that quantum computing promises to us, then we can. When I think that will be a fair comparison. Because we are in the moment that quantum computing is not in its completely and finished form. So maybe it's not a fair comparison because you are comparing a mature technology with a new one. So
okay.
I don't know if we have to do this comparison in a philosophy way.
Maybe I will also later summarize this and add one suggestion, but I see that Daniel would like to say something, I guess.
Forgive me if this sounds stupid, but it reminds me of a debate between Elon Musk and Jack Ma of Alibaba. So Elon Musk was talking about the advances of artificial intelligence with the example of the AI beating the best Go player, and Jack Ma's argument was that the game of Go was not complex enough to what's the word, to compete with, to be compared with the human brain, like the complexity that the human brains can solve. And so is it that you guys are debating about a problem between a classical computer and a quantum computer, but that problem is just not complex enough that a quantum computer can show the clear advantage? Is that like relevant?
Yes, that's absolutely true. I mean, we need to dig dig into the theoretical parts to make this clearer. But the point is, NP complete and NP hard problems are most likely not complex enough. So there are different and more complex problems where quantum computers indeed could help, right? So they're then usually not part of the NP complete set of problems. And So your analysis is totally right.
Okay, great. So maybe let's maybe try to summarize. I guess that the good summary might be that for sure we should understand that this is a research phase, and it's important to do a research. But on the other hand, I think that I can also agree with Sebastian that it's always good to do comparison with classical algorithms, because most likely we'll know that classical algorithms, so the outcome will be that the classical algorithm is still better, but at least we'll know how far we are and what's the reason why classical algorithm is better, whether it's just a matter of the hardware, that it's still not perfect and it may change in the future, or maybe there are some other reasons, just due to, let's say, some theoretical properties of a given algorithm. So I think that from even from a research perspective, I think that I can agree with Sebastian that it's good to do comparisons with classical algorithms. But anyway, it's very important to do such a research, and it's very good also to hear and to have such discussions. And I guess that, as Shahin said, maybe we should even organize a separate meetup just to discuss this topic, right? So regarding this quantum advantage and how to conduct such experiments in a proper way, let's say. So this might be also a good idea, as also Martin confirmed, I guess. All right, I think that we should move forward because we've already spent a lot of time on this discussion. So if you don't mind, let's try to ask some other questions, because there are still a few. So
Although,
there is
sorry,
yes,
I think Dr. Farbod wanted to say something, and don't know if he's still up, but.
Thank you very much.
Yes.
Can I talk now?
Yes, yes.
It's very, very hard to say something, sorry. Okay, so I think Sebastian's question is very general and is not related to this specific presentation. So the presentation is great, and I really enjoyed it, and thank you for that great presentation and great work. But the question for quantum computing is a general question, and Shahin already answered the question. I think that was the best answer, which is the exploring the area. Now the question might be, okay, we have to explore the area at what cost? So you say, for example, United States is investing $1 billion maybe on quantum computing to explore if quantum computing is better than classical computing. And we still accept one particular algorithm, or one or two, which is like Shor's algorithm. We don't have any proof for any algorithm or any kind of quantum related computing that can perform better than classical. So now the answer, I think, after I talked to several people, I think the answer is competition. So who is going to achieve quantum supremacy in terms of which country is going to achieve this first? And why do we need this competition? Because people are scared if one country achieve the quantum supremacy first, okay, so they may achieve something that maybe in terms of even military, for example, quantum cryptography and all these things, then maybe they can rule the world. So that's something that maybe when I discuss this with other people, like even in military or leaders in quantum annealing, for example, I know, as you know, for example, D-Wave is known for quantum annealing. And when I talk to the people who are leading the projects, so person who is leading the quantum D-Wave computer, he says that, okay, we are trying, but we still don't have that much proof that quantum optimization is better than classical. But I think it's all about competition, and countries are scared from each other. Who is going to achieve this first? And exploring is always good, but at what cost? That's the question. Okay, thank you.
Okay, thank you. All right. Yes. So I think that we should move further to some other questions as well. There is a question from Daniel Handias. Maybe it's also related. I'm not sure. Can it be that this problem is just not complex enough to give
yeah,
quantum?
That's exactly what I said. Yeah, it's okay.
Yes. Okay. Okay. So it's already asked, and Do we have any more questions? Yes, there's a question from Itamar. Can various ansatz formulations overcome the limitations due to number of qubits and noise?
Can you repeat the question, please?
Can various ansatz formulations overcome the limitations? I'm not sure what limitations were in mind here, due to the number of qubits and noise. So it was a question posted by Itamar Halevi. So Itamar, if you are still with us, maybe you can clarify.
Well, that's related in a way to the previous issue, but I asked it before that started with Sebastian. And the thing is simple. There are hardware limitations at this point, and they are focused on number of qubits, which is limited, and also instability due to noise, and also to the nature of the qubits that are not stable over time. The question is, maybe we can improve and deal with these limitations by different theoretical ansatz, because ansatz is not carved in stone. It's based on intuition of one researcher versus others. In other words, there is room for different variety of ansatz with naturally different outcomes. It means that the experimentation is not ending in one model or in one approach, because I can come tomorrow with another ansatz and my results will be different, better or worse, I don't know, because I haven't done it. But I'm just considering different forms of ansatz, because they reflect certain different intuitions and understandings about the problem, either the specific problem or the general.
Okay, we are trying to suit our answer to our problems, but there is a big distinction with the answer that you can make for quantum chemistry, for example, when you have a when you choose the Hamiltonian for the molecule, for example, because every problem has different weights and different containers. So it's very difficult to choose a really tailored answer for the problem, but we experiment a lot with different answers, and in this context, with this amount of noise, we choose to do minimal and to perform minimal answer in the way that we choose to put the less gates than we can, and with this approach, we have the best results of finding the optimization value.
Okay, thank you.
All right. Thank you, Itamar, for this question. And thanks, Laura, for a great answer as well. Okay, do we have any more questions? I can see that there was even a question, what does a quantum computer do? But I think that there should be also another webinar about it.
I think that is a question for all
yes.
that are here, not,
yes,
not only for me, please, because they are so general.
That's true. So there should be. So this is a question whether we really understand what quantum computers can really do.
I think after the meetup that we could organize with Sebastian question, we have another one talking about theory of computation and what is possible.
Okay. All right.
By the way, I just want to add something. Rafael, Martin, and Laura, first of all, I admire your efforts, and I would invest in your company any day. Quantum, to argue that we shouldn't do something because it's not better. It's like saying when we tried to go to the moon, you know, Elon Musk's spaceship blew up 3 times, and the 4th one, it succeeded, right? So this argument that quantum computing is not outperforming classical computing is to my mind illogical, right? If you look at the history of human progress. So I support what you guys are doing, and if I have a chance to invest, I will invest.
Thank you.
Thank you very much. And we are enjoying it very much. So that is another reason. We are enjoying working together and studying, and well, knowing all of you. We are meeting a lot of people all over the world. So it's for us, it's an incredible experience.
All right, great. All right, are there any more questions or last comments, remarks? I don't see more questions now on our chat, so I think we can finish. So thank you once again for participating. So first of all, thanks Rafael, Martin, and Laura for such a great presentation and also answering all the questions. So we really had a very interesting discussion here. We also would like to thank all participants and also all people who asked some questions. Maybe before we finish, I will just share my slides for the last time, just to invite you for our next meetings.
Excuse me, Pawel, let me thank the audience. Let me thank you, the organizers, before you invite to the next one.
Okay.
And let me thank you, the organizers and the audience. And thank you for, especially for the audience, for the commitment with our presentation, the attention, and very interesting questions, both technical, that go to the detail of a formula, a specific formula, and the interpretation of it, and for general terms about quantum computing capabilities and so on. So thank you very much. It's very, for us, we enjoy it very much, and makes us, we encourage to continue studying and working together, well, and be part of this community. Thank you.
Great, fantastic. Thank you. So yeah, we hope to see all of you, and please also feel free to invite your fellow colleagues, researchers. We would like to invite you to attend our next meetings. So the next meetup will be on 24th of July, circuit mode of quantum computing as if it occurred in an escape room. So looks very interesting and inspiring. Let's see. The next meeting will be in August. The title is Quantum Multi-Body Dynamics, Robotics and Autonomy. Also, we'll have some meetings in September, quantum computing for quantum chemistry, and there will be quantum machine learning lightning talk. So this is a meetup that we had to postpone in April. So most likely it will be organized in September. And at the end of September, there will be one more meetup about quantum communication. So we would like to thank also all the organizers and our sponsors, supporters, Quantum AI Foundation, Warsaw Quantum Computing Meetup, Harrisburg Quantum Computing Meetup, Alexandria Quantum Computing Meetup, Quantum Computing and Data Science Meetup from Toronto, Brooklyn Quantum Computing Meetup, Orion X, and Association Quantum. So we all organize this meetup together. We all make it such a good experience for everyone. So we hope that you enjoy our meetings, and we'll have the opportunity to meet again in the future during our next events.